All right, our next concept in this unit of equilibrium is looking at weak acid equilibria. Now, if you have a strong acid, as we just saw in the previous lecture, like HCl, strong acids completely dissociate. And because of that, the amount of H plus, and again remember, H plus is the same as hydronium, the amount of H plus in the solution is exactly equal to that of the strong acid if it's a monoprotic acid, which means there's one single proton that it donates per particle. The only strong acid that we have is sulfuric acid, which can donate 2 protons per particle, but we'll talk more about that later in the lecture. For the most part, almost all strong acids are monoprotic, and therefore the concentration of the label, on the label of the acid, is also the concentration of the H plus concentration. And therefore, if you take the negative log of that, the pH of a 0.5 molar HCl solution is got a pH of 0.3. Okay? Now what happens when we have a weak acid? When we have a weak acids only partially dissociate, and therefore we see a double-sided arrow. I would prefer when you do the general equation for a weak acid that you do not use the dissociation without the water. I would strongly recommend that you do the reaction with water, because then it's going to be exactly the same as what we do for weak bases, and therefore you don't have to worry about when do I include water, when I don't. I just strongly recommend you always include water with your reaction. So the weak acid will donate an H plus to the water. Not much, but to a small extent it does, and usually this is going to be less than 5%. But some of the donation will occur, and therefore you will have a concentration of H3O plus, and because HA, which is the general formula of the weak acid, what we're left with is the conjugate base. HA is the general formula of the weak acid. A minus is its conjugate base. So once we remove that proton, what's left behind is the conjugate base, which is A minus. Again, that's just a general equation for it. These are on your green sheets as well. Okay. So Ka is really a Kc expression, which means we're going to use concentrations. A Ka is the weak acid dissociation constant. The higher the Ka is, or the bigger it is, the stronger the acid. So acids that are strong acids have Ka values that are greater than 1. Acids that are weak acids have Kas less than 1 because a small percentage of it dissociates. And the smaller the Ka, the weaker the acid is. All right? Okay, so the first thing I'd like you to do is to write the acid dissociation for acetic acid in water. Write the acid dissociation equation. So here's the general equation. Now write it plugging in not HA, but the actual true formula of the acid, and then write the Ka expression of it. So I'm going to pause the lecture now. Go ahead and do that and see if you can get it correct. All right, you should have had acetic acid react with water in equilibrium to reduce the hydronium ion and the acetate ion. To write the Ka expression, we have the height of the products on top over just the weak acid. Acids are always aqueous, AQ. Because it's aqueous, it does get part of the Ka expression. Water is a liquid. Okay, and again, anything that's a liquid or a solid is not part of a Ka expression. So this is an example of a Ka expression where we're looking at the concentration of H3O plus with conjugate base over the weak acid. Okay, now I've given you the steps on how to do a Ka problem, which is nothing more than just doing an ice problem. So we're going to do the same exact process we did as the previous chapter 15, but now just apply it to an acid versus to a gaseous substance. Okay. One last thing, a couple other things, general equations. There's something called pKa, which is nothing more than the negative log of the Ka. As I've already said, the higher the Ka value, that leads into a stronger acid. Well, if I take the negative log of a bigger number, we end up getting a lower pKa value. So if you're not given the Ka of the acid but the pKa, the lower the pKa, the higher the Ka, and then therefore the stronger the acid, and vice versa. So again, and you're going to see where this comes into play next week when we start talking about titrations. But the pKa allows me to figure out the Ka or vice versa, and it allows me to look at a relationship. Just like pH. the more H plus that's in the solution, that leads to a lower pH. Same thing here. A larger extent or dissociation of the weak acid will produce a lower pKa value. Okay? So in general, the weaker the acid, okay, the lower the Ka value and the larger the pK value is. It's an indirect relationship. Okay? One last thing is the percent dissociation or ionization. This is looking at what degree of the acid dissociates, producing the hydronium ion and the conjugate base. How much of this has dissociated? So if it says that 5% of it has dissociated, if I'm starting with a 1 molar concentration, that means 5% of it is dissociated, which would mean I would subtract 0.05 molar of it, and this would go up by 0.05 molar. Because 5% of 1 is 0.05. So that would mean that there would be 0.95 molar left and 0.05 molar of each of the products. So if I know the amount of dissociation, that would tell me then the percent ionization. So again, you can see that by looking right here. How much H3O plus did we get in the solution? And what was the initial concentration of the weak acid before any dissociation took place, times 100. And that'll give us the acid dissociation. So on the national exam, if they tell us what percent of the acid is dissociated, we can immediately figure out how much is left and how much H3O plus is produced and use that to be able to figure out different variables in the ice table. All right, let's turn the page. Okay, so the first problem here is looking at a student prepared a 0.1 molar solution of formic acid and measured its pH using a pH meter. The pH at 25 degrees Celsius was found to be 2.38. Okay, calculate the following. All right, just like all ice problems, the first thing you should do is write the dissociation equation. And again, all acids are aqueous, so we'll label with AQ. We're going to include water for all of these. The acid will donate the proton to water. Oops, and I don't need to put aqueous if it's an ion already, my fault. Okay, now, in order to do problems, just like we've done before in chapter 15, the next thing is to write the word ice next to it. Okay. They have told me that the student made a 0.10 molar formic acid solution. Anything that's labeled with an L or S, solid or liquid, we cross out of the table. All right, and what we assume as we make it that initially the concentrations of these ions are 0 before any dissociation starts to take place. Then a certain amount of dissociation will take place, and that's where we can utilize the ice table. Again, because there's no products, some of the acid is going to dissociate. And the value of E is just simply now those numbers, those two columns, the I and the C added together. Now, what's the last piece of information given? They tell me that the pH is 2.38. Well, if I know the pH is 2.38, what can I use that information for? What will that allow me to figure out from the previous lecture? Hopefully, you're saying that if I know the pH, I can figure out the amount of H3O plus that's in the solution. So, and once I know that, that'll tell me this number right here, the amount of H3O plus at equilibrium, because that's the pH of the solution, and that'll allow me to now figure out all of the different values in the table. So let's go ahead and do that then. If you want to pause the lecture now, maybe you want to decide to do that too, and see if you get it right. So 10 to the negative pH will give me the concentration of H3O plus. So we get a concentration of 0.00417 molar. Okay, that also tells me the value of X, right? So then if I know that, I now know the value of this guy is 0.00417. This guy is 0.00417. And this guy will be 0.1 minus 0.00417, which gives me a value of 0.0958. So now I know the concentration of all the substances once equilibrium is achieved, right? And now because of that, I can now calculate the Ka. The Ka will be products over reactants, so it's going to be 0.00417 squared because there's two of them. We're not going to multiply it by 2, but it's like x times x, which is x squared, over 0.0958. And we get a Ka with a value of 1.82 times 10 to the negative fourth. Again, when we are working with weak acids, we expect to have the Ka value be less than 1 because a small percentage of it only dissociates. Okay? Now, what percentage of it has dissociated? That's the next step of the problem. So, in a weak acid problem, if they give you the pH, the first thing you can do is figure out the H plus concentration, which then usually gives me the value of X. I can then figure out the remainder of the equilibrium concentrations of all the substances at equilibrium, and then I can plug those into the Ka expression. Again, it's a matter of just doing a bunch of practice that you get very comfortable doing this and get really fast at doing it as well. All right, letter B, what percentage of the acid is ionized? So, again, the percent dissociation or ionization. Okay, how much H3O plus is in the solution? So what is the amount of H plus in the solution at equilibrium? Divided by the initial concentration of the acid times 100. And we get 4.17%. As I said, you can often expect that the amount of ionization or dissociation of an acid to be under 5%, which indeed this is an example of an acid that does such that. Okay, so that's an example of how to do a weak acid problem, right? So if you want right now, go ahead and pause the lecture and try to do the next 3 examples on a scrap piece of paper. And then when you are done, start the lecture back up again. I will already have all the work provided, and then you can quickly check your answers to see if you get them right. All right, so go ahead and pause the lecture now and do that, please. All right, looking at the problems here, again, in a typical weak acid problem, you've got the weak acid plus water produces hydronium and the conjugate base. Again, usually the molarity is given and the initial concentration of the hydronium and acetate are 0, 0. Some of the weak acid dissociates minus X plus X plus X. This is the nice thing when we have monoprotic reactions where there's only one donation of one proton. So we always get the initial concentration minus X, and we get X and X. In this problem, we now plug into Ka, which would be X times X on top, X squared over 0.3 minus X equals Ka. Plugging into the Ka expression. Because the value of Ka is on the order of the negative fifth, the rule of thumb is if the Ka is on the order of the negative fourth power or smaller, negative 4, negative 5, negative 6, the 5% rule will work. If we go any bigger than Ka of a negative 3, negative 2, too much of the acid dissociates and the 5% rule is not validated. We can't use the 5% rule unless Ka is at an order, a magnitude of 10 to the negative fourth or smaller. This one is negative 5, so we can do the 5% rule, which then gets rid of the X that we add or subtract from. So we now have Ka equals X squared over 0.3. Solving for X, you should get 0.00232. And taking the negative log of that, we get 2.63 for the pH. And taking that number divided by the initial concentration of the acid being 0.3 times 100, we get 0.77. Under 1% of the acid has dissociated. In the next problem, we're utilizing the fact that we kind of just like the example I did way up here in A. I know the pH is 5.87, so if I take 10 to the negative pH, that gives me the H plus concentration. And in these problems, that gives me the value of X. So I now know the value of X and I know the conjugate. Now, while I realize that this is a different reaction, it's always the same. The weak acid plus water produces H3O plus and the conjugate base. So I know the value of X. So if I take 1.35 to the negative 6 and square it, that's divided by the initial concentration of the acid, which in this problem is 0.25, minus the 1.35 to the negative 6, and that gives me the Ka of 7.28 times 10 to the negative 12, an extremely small Ka. The percent dissociation would be the 1.35 to the negative 6 divided by the initial concentration of the acid being 0.25 times 100, and we get 5.4 times 10 to the negative 4th percent. And that's a percentage. So we're looking at, again, a value in which is on the order of something that is extremely, extremely small. Letter C. Here they've told us the percent ionization is 0.038%. And now what we're trying to do is figure out the pH at the equilibrium. Again, the weak acid is 0.75. The initial concentrations are 0, minus X plus X. If I take 0.038%, and again, you have to be careful. We've got to get it out of percentage mode by moving it 2 to the left. So it's 0.00038 is it out of percentage mode, times 0.75 gives me a value of 2.85 to the negative 4th. This is the amount that decreased, which is the value of X, which also tells me now the concentration of the H3O+. So now if I take the negative log of that number, I get a pH of 3.55. To get the Ka, just like I did before, I take that same value, square it, and I divide it by the initial molarity minus it to get the Ka. So here are really the three classic types of problems you could be given on the national exam when it comes from weak acid. If you know how to do all three, you just follow the same exact steps just for a different acid that has different numerical values. All right, so what happens when we have a polyprotic acid? A polyprotic acid is one in which it can donate more than one ion. In this case, carbonic acid has the ability of donating 2 protons. Phosphoric acid has the ability to donate 3. Now, what doesn't happen is it doesn't donate both or all 3 all at once. Each donation of the proton occurs in a single step. So this would be the donation of the first proton, and then this is the donation of the second proton. So the carbonic acid produces one proton that is grabbed up by a water molecule, and then the subsequent substance has the ability to provide one more proton, and another water molecule would pick that up. So what you'll notice is the first Ka, the first donation compared to the second, you notice it's on the order of 10 to the 4th. What does this mean? This pretty much means that almost all of the H plus that is provided by the substance occurs in just the first donation. So if we have a polyprotic acid, we don't even necessarily worry about the second donation at all, because the amount of H plus that we get from it is so small that it really doesn't change the number of the H plus at all from the first one. It's like having something where we have 0.05, and then we're going to add to it 0.000000485. The number still, when we add them together, is still pretty much 0.05. So the first association is the only one we have to worry about. So treat a polyprotic problem just like a monoprotic one. Just do the first dissociation of the proton, and you don't have to worry about the second one. So I'm going to go ahead and prove this to you with a mathematical problem. So here we said the solubility of CO2 in water provides a molarity of 0.0037 molar carbonic acid. Okay. The common practice assumes that all the dissolved CO2 forms carbonic acid, which is produced by the reaction between the two of them. What is the pH of a 0.0037 molar carbonic acid solution? Okay, well, the carbonic acid in water will donate a proton, producing H3O+. and we get the bicarbonate ion. Again, we'll do an ice problem here, in which we have 0.0037 molar. The water's crossed off because of the liquid, and we get 0, 0, minus x, plus x, plus x. So we get 0.0037 minus x, x, and x. The Ka for this expression for the first association is 4.3 times 10 to the negative 7th. I plug in my values. X times x gives me x squared over 0.0037 minus x. Can I use the 5% rule? Is Ka small enough? Yes. The 5% rule is valid because Ka is on the order of negative 7. So that means anything that we add or subtract from initial concentration is so small that it's negligible. So I get rid of the x on the bottom, and so then I get 4.3 times 10 to the negative 7th equals x squared over 0.0037. All right, so let's go ahead and do the math here. I get an x value, which is 3.99 times 10 to the negative 5th molar. All right, so that is the amount of H3O plus that is produced by the first dissociation. And as I said, since the first dissociation pretty much produces all of it, I can now go ahead and calculate the pH of this solution. Because this is the value of x, which is the amount of H3O plus that's in the solution. And so I get a pH of 4.40. Okay? Now, this is all I'd have to do in order to figure out the pH because this second dissociation is so small. But they're asking in part 2, what would be the amount of CO3 minus 2 that is produced? Well, in the first association, I get 0 CO3 negative 2 produced. So to figure out the amount of CO2 that's produced, as you can see up here, I would have to do the second dissociation. So now the HCO3 minus 1 would have to further dissociate, by reacting with another water molecule and donating its second proton. And this would produce the CO3 molecule. Again, we'll cross off the water since it's a liquid. Well, what is the concentration of the H3O plus negative 1? Well, that is also the value of x from the previous problem. So this concentration is 3.99 times 10 to the negative 5th. This is a mistake students make. Right away, students want to do 0, 0. Here's the problem with that. The amount of H3O plus is not 0 now because just like the bicarbonate ion, the hydronium ion was produced in the first dissociation. And we can't get to the second one until the first one is complete. So we also have 3.99 times 10 to the negative 5th molar hydronium because that's what the value of x was from the previous one. Did I get any CO3 minus 2 from the first dissociation? No, so that is 0. And since it's 0, the acid can further dissociate to get some extent of CO3 minus 2 present. Adding these guys together, 3.99 times 10 to the negative 5th minus x, 3.99 times 10 to the negative 5th plus x, and x. So now I'm going to go ahead and throw these numbers in to the second Ka expression, which is Ka2, which has a value of 5.6 times 10 to the negative 11th. On top, 3.99 times 10 to the negative 5th minus x, plus x, my fault, plus x, times x, all over 3.99 times 10 to the negative 5th minus x. I'm just plugging in my values into the K expression. The two products go on top, and the one reactant goes on the bottom. Can I use the 5% rule? Oh, heck yeah. The value is negative 11. That is extremely tiny. Very little of it is going to get to this level of dissociation. So I get rid of the minus x, But I also get rid of the plus x on top because both of these have an initial concentration something other than 0. So I get rid of both x's, and because I do that, what am I left with? 5.6 to the negative 11th equals 3.99 to the negative 5th times x over 3.99 times 10 to the negative 5th. Well, look at that. These two numbers also cancel out because the same number divided by itself. With all of that work, I end up getting an x that is 5.6 times 10 to the negative 11th molar. And the value of x does give me the amount of carbonate ion. So the amount of carbonate ion that's present in this solution is this molarity, an extremely small amount of carbonate ion. Okay? But I'm also going to prove a point to you now. So actually the H3O plus concentration is not 3.99 to the negative 5th. It's really 3.99 times 10 to the negative 5th plus 5.6 times 10 to the negative 11th. And so if I add these two numbers together, I get 3.9900056 times 10 to the negative 5th. If I were to round to 3 sig figs, I get the same number. What I'm trying to do to you right now is to prove a point. When you have a polyprotic acid and you're asked to figure out a pH or amount of extended dissociation, you only look at the first one. In phosphoric acid, you'd only do the first dissociation where H3PO4 becomes H2PO4 minus 1. You only do the first donation because, as you can see again, the second one is on the order of -5 or 5 powers less likely to occur. So almost all of the H plus that is produced and what the pH of the solution is solely dictated by the first dissociation. Okay, so that's how you do polyprotic problems. So in Canvas, there are practice worksheets on monoprotic acids and polyprotic. But even if it's polyprotic, all we do is like I did for this first problem up here. I just do the first proton donation, and that's all I worry about, and I figure out the pH from that, and I'm done. Okay? All right, there's also these other problems here in the packet that I'm going to pause the lecture. I'm going to complete these, and after I complete these, I will post these. And then you can take a look at these. Again, you can start the lecture up. You'll see all the answers. And then you can continue to work on more practice problems in Canvas where I have an additional set of worksheets on monoprotic and polyprotic examples and the answer keys to them. All right, so I'm going to pause the lecture now, work out these problems, and then show it to you real quickly, and that'll be it for today. All right, the solutions, as you can see, are present up above. The first problem, you had a solid state material, so you had to first convert it into the molarity. Again, I'm always using the equation Ka, concentration of H3O plus, conjugate base over weak acid. So I'm constantly using this equation. I'm just not rewriting it over and over again because I don't need to. This equation is also on the green sheet, so it literally becomes mostly just a plug and chug. What are all the variables that you know? When I am given the pH, I know both the concentration of H3O plus, which is also the same as the A minus, because they're both X and X in the ICE table. So when I go ahead and plug in all the variables and solve, again, don't forget to do the subtraction here because we're actually fairly close to it. If you forgot to subtract off the value, because in the ICE table, it's the initial concentration of the acid, okay, whatever that number is, minus the X, which in this case is the 0.00251. All right, and we get a Ka of 3.61 to the negative 4th. Second problem again, we know the Ka. We can do the 5% rule, which gives me a value of X of 0.00775, which is the concentration of the H2O plus. The negative log of that gives me a pH of 2.11. And again, the last problem, again, it's a carbonic acid problem. It's a polyprotic acid, but I'm only worried about the first dissociation where it just loses the first proton, as we saw in the previous problem, and therefore the initial concentration minus X and X and X. Again, we're seeing the same scenario over and over again, which hopefully should make it easy for you guys. We'll use the 5% rule, and that gives me a value of X, just like the previous problem, and a pH of 4.68. Again, I don't have to worry about the second dissociation where the bicarbonate further dissociates, producing the next proton, because the amount that we get is so small that it really doesn't change the pH at all. Okay? So those are the problems in weak acids and weak polyprotic acids. Let me know if you have any questions. But otherwise, it's a matter of you guys just doing lots of practice problems, gearing up to take the exam in a couple weeks.